Imagine a robot is performing simultaneous localization and mapping using pose graphs. As the robot moves, more nodes are added to the pose graph, increasing its size. This pose graph must be reduced if the robot will navigate for long time periods. In this work, we explore node marginalization to remove nodes from the pose graph while minimizing information loss. The state-of-the-art technique which maintains pose graph structure is nonlinear factor recovery, or NFR. While NFR is proven optimal, it is computationally intensive, as it attempts to solve a convex optimization problem on the space of positive definite covariance matrices. Another commonly used technique for removing nodes in a pose graph is pose composition, or PC. After removing x0, PC composes the original relative poses between x0, x1 and x0, x2 and computes the new edge between x1, x2. PC is widely used due to its simplicity and speed. However, while it is optimal for a simple two-edge graph, many note PC is not generally optimal due to information duplication. To demonstrate, let's remove a node with three neighbors. In this example, we compose edges x0, x1 and x0, x2 to compute edge x1, x2. Similarly, we compose x01 and x03 to compute x13 and compose x03 with x02 for edge x32. Notice each original edge has been used twice. This eventually makes the composed graphs overly confident. To solve this, we split each edge into two edges, scaling the original information by half, and composed these sub-edges. However, we discovered the optimal scale factor is not 1/2 but 2/3. This scaling factor also applies to other graph topologies. We then explored another idea using the relative pose reparameterization of the absolute pose graph. To recap, we want to remove x0 from the original pose graph on the left to obtain the pose graph on the right. Notice each absolute pose graph is equivalent to an independent distribution of the relative poses corresponding to its edges. Using this, we convert the distribution of relative poses on the left to the one on the right by combining all relative poses into the same graph. Next, all unwanted variables are eliminated to get a dense Gaussian distribution on nodes of interest. We can then optimally approximate the dense Gaussian by the product of marginal distributions, which is exactly equivalent to PC. Unfortunately, our dense Gaussian distribution may be degenerate, indicating the product of marginals is not optimal. We observe that the joint distribution of each set of non-degenerate relative poses can be optimally approximated by the product of marginal distributions. By leveraging spanning trees, we have three choices of marginal approximations using any pair of two variables, while the third variable captures a pairwise correlation. By combining all spanning trees and their marginal approximations in the graph, the scale factor of 2/3 is recovered. Our contribution is a general formula to find the scale factor, which is the number of spanning trees containing an edge divided by the total number of spanning trees of the targeted absolute pose graph. That formula exactly matches with the optimal scale factors we discovered in our experiments on the simple pose graphs. On real datasets, our method computes in fractions of seconds, where NFR may be computationally unusable. Our method also produces generally better results than PC. However, our method is not generally optimal. Our results for the dense target topology are expected to be better than the tree topology, but are actually worse. The hunt for a fast and optimal approach continues with optimism.